For those of y'all not familiar, we have about 10 tenure track faculty within ISIS, mostly in ECS, and the primary focus of most of the research that goes on within ISIS is around CPS. So that's what I work on, and my particular focus is on verification for CPS. So that's what we're going to talk about today, why that's important, and some results, and see what that's about. So what are CPS? So these are modern embedded systems where we have some physical environment, maybe some humans involved, as well as a control theoretic plant typically, because we want to control something in the physical world. And then we interface with that physical state through sensors and actuators. And then this is controlled over software, and all this stuff might be networked together. So there are a lot of examples of these things, from drones to smart cities to smart homes to modern cars to Internet of Things. The major CPS publication venue is the Cyber Physical Systems Week. In 2019, it's going to be the CPS IoT Week. So it's sort of trying to get some more evolution into IoT since that term also arose. So the question we try to investigate within our work is, can we bet our lives on such cyber-physical systems, because many of them are safety critical, and as we'll demonstrate with some motivation, sometimes we don't fail to design them such that they operate properly in all scenarios. So that's the verification problem. The more common term, so I really work on formal verification, but the more common term is verification and validation. And I'll define what these two things are if you haven't heard of these, but it seems like within SimCenter there's some work on these types of challenges within systems, trying to make sure you've built the correct system and that it does what it's supposed to do. So I'd like to verify that CPS satisfy their specifications, typically some safety specs for these type of safety critical systems, security specifications, and other requirements. But typically they're complex. We're building ever more complicated systems, as demonstrated, not with a perfect metric using lines of code as a metric of complexity, but our systems are getting exponentially more complex. This is just a demonstration for aerospace systems on the order of, for aerospace and automotive. So I think the F-35 is another about order of magnitude more lines of source code in the software design for that. So that's basically what's on this one for the F-35, just kind of demonstrating an exponential growth in the complexity of these systems. And this kind of goes in, I forget whose law it is, but there's a law that software gets as complex as the amount of computing power you have that could support it, right? It sort of bloats to fill up however much you'd had. So this kind of goes directly in line with Moore's law. We've got exponentially increasing computing power, so our software is getting also exponentially more complicated. So what we work on within this context is V&V. So what do we try to do in this? And this in particular is a formal methods approach to this. So I'll tell you all a little bit about formal methods. Just show of hands, who knows anything about formal methods? Anybody heard that term? Like 2 people, 3 people, okay. So it's a small area of computer science, but one that probably has more impact per capita than many other areas. Lots of Turing Awards within this area, from Dijkstra to Ed Clark, a variety of people. And also, you may not know it, but all the computers that you rely on every day were built in part using formal methods. So all semiconductors these days, all semiconductor companies, Intel, AMD, Apple for their custom designed chips, Qualcomm, everybody applies formal methods and model checking in the design of modern microprocessors. And they buy software from companies like Mentor Graphics, Synopsys, and Cadence. So those are big EDA vendors. So you do rely on these things, and it essentially what the problem that is addressed by pieces of software. There's some interesting history that I won't get into of why they do this in the semiconductor industry. But the basic problem is we have some model of a system and a specification or requirement or property. We'd like to have a method, ideally an algorithm, but often that's impossible. But a method, hopefully that would terminate to show that the system model satisfies the specification, typically written like this. And if so, we get some evidence, possibly a mathematical proof as to why it satisfies it. Or if not, we have a bug or a counterexample, and we can go back and try to fix either the system or the specification. So in engineering in CS, this V&V problem really is a grand challenge. These are just some metrics on the amount of effort this process takes in system design. So at a company like Google, typically there would be one software tester per one software engineer, so about 50% cost is spent on V&V. At a company in the aerospace domain, the typical figure from our NASA collaborators is for every $1 spent on design, there'll be $8 to $9 spent on V&V. Right, so that's sort of getting towards 90% of effort is not in designing a system, but actually trying to solve something akin to this problem and certification issues as well. So we do fail to do that a lot of the time, and I've got a lot of motivation as to how we fail. So a decade and a half ago, the cost to the US economy of this was about $60 billion a year using this now outdated NIST study, but you can imagine how much software we depend on every day. And I'm sure if I ask how many people in the room have ever experienced a software bug, everybody's hand goes up. Then within academia, there are also some fundamental and foundational reasons to study this. It's computationally hard. So I mentioned if we could come up with an algorithm. So for most interesting classes of systems, like how we would model CPS, this is actually undecidable typically. And then ways that we would try to evaluate this, the complexity of trying to solve this, even in approximate ways, grows exponentially in the size of this system. So our systems are getting exponentially more complex, and also this V&V process is exponentially hard in the size of the system. So this challenge, it really is a challenge because we're making this V&V process be essentially doubly exponentially hard, right? So we have a lot of work to do. And this is things like trying to identify edge cases and lots of issues. So we work on CPS, so that's our systems here. You can instantiate this system model with whatever you want. In semiconductor, going back to that, this would be a digital logic circuit typically, and a specification as an example, and that might be that if you have two inputs to an adder, that the output is their sum modulo a carry or something, right? So some spec. So in the context of CPS, we may have safety specifications, so something bad never happens. Stability type specifications, which are control theoretic often in nature, like you get to some good set of states and remain there. Those are also called liveness specs. And then we might have other things that our systems should do, like maintain work if hackers are attacking, have performance constraints, and other things like that. Right, so that's what we work on in our group, and our primary focus. So the difference between verification and validation, which some of you, I think, probably know this V model, but verification you can phrase as, does the system meet its requirements, whereas validation would be, do a set of requirements that we've come up with meet the needs of whatever the application or users of that system are. So another way to phrase these as verification is, did we build the system right, i.e. correctly? And validation is, did we actually build the right system? Right, so validation typically is a lot harder, would involve talking with stakeholders, customers, how this system might actually be used. But verification is also very hard. And this is one system engineering model for how this process would go. You start with requirements, documents, and what systems should do, and then go through further sort of iterations of design down to coding, and then maybe work on the verification side of it over here. So typically in modern processes, these things are much more tightly integrated. You can imagine how an agile development methodology might fit into this process. Right, so I'm going to switch a little bit of gears to motivate things after talking about introducing a little bit about what we work on in our group, and then I'll start with why do we work on this and some hopefully interesting failures and recalls and things that you may not be familiar with, some classical ones, that people may be familiar with come from different domains. Things like Therac 25, which is a radiotherapy machine that killed some people back in the 80s, overdosed them with radiation. Ariane 5 is a pretty famous aerospace example, which was a rocket that, European Space Agency rocket, that due to an interesting bug blew up on takeoff. And there's a lot of other examples. You can find tons of interesting lists of examples, but I will share some that hopefully you haven't seen before, so hopefully they'll be interesting. So we work on a variety of types of CPS. One is drones. These are some pictures of some summer undergrad students who worked with me 2 summers ago. And then this past March, some of the students participated in a NSF UAV challenge, which they're always looking for more participants, so something to consider for students here. I think they're going to do it again in 2019. So that was sponsored through the CPS virtual organization, which is an organization sponsored by NSF, like an online community essentially for CPS research. So if you have an NSF CPS project, you have to use this, but there are also other opportunities like this available through it. So this is a shot of our drones in our lab. There are a bunch of different types, mostly quadcopters, a few fixed wing. We have some ground vehicles too. These are mini drones. I had the Tello out a minute ago. Then there's some sort of bigger drones too, like DJI Phantoms. So we use these as case studies in our V&V type work to say evaluate whether an algorithm meets its specifications. These are all control systems, so you can evaluate control theoretic requirements like stability. So great applications. Obviously, I think drones are also cool, so it's sort of fun to play with, a great way to get students involved. So the applications of those, let's see if my video is going to load, which we tested a minute or 2 ago. So the applications of drones, as you might be aware, are fairly broad and are growing. So this is a demonstration by DoD that hopefully will play. Looks like it's just opening a bit. This was done a couple years ago, I think in early 2016, and this is a DoD-built drone swarm called Perdix. Anybody heard of Perdix drones? Okay, 1 or 2 people maybe. So this is deploying, in total these 2 fighter aircraft are deploying about 100 drones. So it's very difficult to see, but they're deploying a drone swarm. So we'll see another shot of it in a second, which will be sort of a centralized command view as the drones get deployed. So these are drones that will fly in green. Things are the drones, and the red points are their currently specified waypoint. So within this, you can imagine different operational requirements or specifications. So they're calling them missions in this DoD context. So all the drones should go to these points. So that's a stability requirement. And the software involved in these things would need to be such that it's actually driving the actuators and sensors, driving the drones in those directions. Then getting them to do kind of a group formation movement, so they're all kind of moving at the same time. And there's some other things you could imagine. When they're still, they're just sort of orbiting. But these are the types of things people have in mind with swarm robotics, types of applications. Obviously lots of defense, lots of other things too, from structural health monitoring of bridges and hard to access buildings to medical supply delivery in remote areas. I'm sure countless things. Photography obviously has a lot of usage of drones. So this is an in-the-field demonstration of a swarm about 2 years ago with 100 drones all launched from fighter jets. So you can sort of imagine the types of things that are possible now. There's a video earlier this year, which I'm not positive about the legitimacy of, but as a headline I saw, there's a boat swarm out of China. Basically the same idea, but with autonomous boats. So all these things, all these systems are talking with each other and coordinating to do something. So that class of distributed cyber-physical systems is one we frequently work on. Right, so there's communication, there's distributed computing, there's distributed algorithms that are being used to coordinate the motions of the robots, to do maybe leader election type of things to get them to choose one of the robots. but to get them to coordinate together safely, obviously things like collision avoidance so they don't run into each other. So a lot of interesting systems. So other domains emerging are things like in vehicular networks, both within a single vehicle or between vehicles. So NHTSA's timeline, the regulatory body for motor vehicles in the US, their timeline for vehicle-to-vehicle communication rollout is in the next few years, essentially, that most new vehicles will have to have vehicle-to-vehicle infrastructure in them. And then within an individual vehicle, a modern motor vehicle has on the order of 50 to 100 computers in it that are connected together over things like CAN buses. So one term that was used in an IEEE Spectrum article is that modern cars are networked computers on wheels, right? So it's maybe a little too far for me to say that. That's why I'm referencing the Spectrum article. But all of the functionality in modern motor vehicles is drive-by-wire, just like modern planes are fly-by-wire. So there's not a whole lot of actual mechanical connection to any of the controls you're controlling or that a computer is controlling when you're driving the vehicle. So you're talking to a computer through a human-computer interface, which looks like a steering wheel. And then things like autonomous vehicles, of course, are on the horizon. So I like to ask this question, and I've gotten various responses back, depending on the audience, oftentimes the age of the audience. So we're sort of mixed. There's some students. So what do we think? The show of hands. There are autonomous vehicles that are being tested on roads today. So from companies like Waymo or Uber or any of the other companies that are developing autonomous vehicles. Are they safer than humans? Show of hands. Anybody? We think they're safer. A few people. Okay. So some think they're safer. It's Friday afternoon. Some people don't want to raise their hands, but really think this. So a standard metric for evaluating automotive safety is the number of fatalities per mile driven. So we drive a lot in the US. If you go look up how much we drive, it's on the order of a half a light year per year in the US, which is mind-bogglingly large. So 3 trillion miles roughly. Annually in the world, it's about a light year. So we really do a lot of driving. So it's mind-boggling, right? We're sort of as many vehicles going everywhere on the earth. So in the US, there are about 37,000 fatalities. So if you divide this out, this sort of standard metric that is used, this doesn't account for non-fatal crashes and lots of other things, is about 1 fatality per 85 million miles driven by humans. And this is due to a variety of things: active safety systems, airbags, passive safety systems, crumple zones, right? So driving is very dangerous. It's the number one killer of people that are about college age, for instance, but still fairly rare. 1 fatality per 85 million miles driven. So if you contrast that to autonomous vehicles, on real roads, currently tested autonomous vehicles have driven about 10 million miles. So they've been simulated for lots of millions of miles, but they haven't actually been tested up to about 10 million miles. And this is across all manufacturers, typically in pretty good weather conditions. So with some of the Uber stuff, there have been some other things that questionably you could classify as being fatal accidents with autonomous vehicles. There was a Tesla autopilot incident a few years ago where someone who had autopilot on wasn't paying attention, and the image classification stuff in the car thought a truck, an 18-wheeler, that the trailer of the truck, it was white, it thought it was the sky and thought nothing was there and ran right into the truck and he died. So there's some instances like that. So if you divide this out, definitely there's 1 fatality caused by an autonomous vehicle, which is the Uber thing earlier this year where this cyclist was hit. So if you compare this now, that's about 1 fatality per 10 million miles driven for autonomous vehicles. Obviously, there's some issues with this type of analysis, but it's sort of a small data set size relative to the 3 trillion miles driven, but it hopefully illustrates where the technology is at today. There's a lot of testing, verification, validation things that need to be done for autonomous vehicles really to start getting shipped. So right now, humans, based on the limited amount of driving autonomous vehicles have done, are somewhere in the order of 1 to 2 orders of magnitude safer. So I'm sort of a pessimist for autonomous vehicles being here. As soon as some projections indicate, I would love to have autonomous vehicles. We can argue about these types of metrics because this can be a little controversial, but this is all based on data. So anyone want to disagree or question things with this? Normally there's a little disagreement. So obviously this is only looking at fatal crashes. This doesn't include non-fatal crashes. That's one limitation. I think humans have about 1 crash per, I think it's about 200,000 or 300,000 miles, something on that. But I was looking at a headline yesterday. I think autonomous vehicles this year in California alone have been rear-ended over 50 times. So you can ask, well, it's not their fault necessarily, but but there's some things. So that would be about, if they've driven 10 million miles, that'd be about on the same order as humans. At any rate, so why are these types of things happening? So one reason, going back to that Tesla example, where the truck trailer was misidentified, has to do with these systems being dependent upon things like image classification methods. And things like modern image classification methods are often AI-based, and in particular, let's say neural net-based. And such systems are vulnerable to what are called adversarial attacks. So these are 2 instances from this Lab 6 website, 2 interesting instances. The top one is demonstrating a 3D printed turtle that's being fed, the video data is being fed into a classification method, and then they add a adversarial perturbation to this model. Basically, we can't see it, but they printed some dots or something on that turtle in addition to just the turtle. And now the classifier is classifying this turtle, which we would clearly say as humans as a turtle, as a rifle, pretty much all the time. Right, so you can imagine the types of issues that can occur in realistic scenarios. Not only things like what happened with the Tesla and the truck trailer, thinking it was the sky due to not reflection, but due to the lighting conditions and other things. There are also actual security concerns for these types of things. What if I start selling clothing that has this adversarial model in it, and now none of the clothes that I've sold, none of the classification methods identify those people as pedestrians now. So autonomous vehicles might not be able to see those pedestrians or classify them as pedestrians. So this bottom one is just doing one on a picture, which is where these things typically have been illustrated with things like Google's image classification methods. So this one's turning a picture of skiers into a dog, that the classifier would think now that it's a dog and not a skier. And I say think loosely. But this one I think is really interesting because that's actually 3D printed, right? That's not just something in a picture where pixels are being modified. And there's a lot of reasons for this. Understandability of neural net type models, errors, environmental modeling, potentially having unpredictable behavior, training data sets. If these things are data-driven models that have been created, those data sets are necessarily incomplete, and you might underrepresent some very critical conditions. So these types of components, as we start to put them into CPS, and the term we're using for these things these days are called learning-enabled components, if you imagine, say, the pedestrian detector in an autonomous vehicle. Right, so these type of learning-enabled components are especially going to be very challenging to put through a V&V process. Okay, so how else have we failed to solve that V&V challenge for real systems? Probably some people know of this Jeep incident a few years ago. So this was a Wired article. There were 2 people essentially from Twitter who in their spare time do car hacking, and They identified a purely over-the-air remote attack where if you could identify this vehicle on the internet, the vehicle's internet connected, if you could find its IP address, you completely, without any physical access to the vehicle, could get internal access to the CAN network and then control things like the brakes, right, or other pieces of it. So this is a major security issue. It's purely over the air, so you don't have to have gone in and done anything to modify this vehicle, like gotten internal access to the CAN network or something and done something physical to it, which is sort of an especially scary incident. So not only are there security issues like this, but this type of defect does exist and resulted in a recall. So people remember this thing? This is a pretty famous thing that happened a couple years ago. And the results of this were, in addition to this Wired article, were presented at the DEF CON or Black Hat security conferences. So in other systems, even in highly regulated systems, we may sometimes fail to solve this V&V challenge, like in aerospace, which is probably the gold standard for software safety. So this is just an instance of a Bombardier aircraft that had a timing error that could cause it to lose spoiler functionality, which would affect controllability. So I'm going to go through all these motivational examples quickly so I can talk some about what we do to try to address some of these things. Non-autonomous vehicles, of course, have plenty of issues. Priuses a couple years ago, this is a really interesting failure actually in the hybrid drivetrain of a Prius, because it's a hybrid vehicle. The software used to control a step-up voltage converter, a boost converter in the hybrid drivetrain, so it increases the voltage. The software could drive the power transistors in this boost converter into a thermal runaway mode. The packaging could then melt, and then the packaging of the transistors could melt, and then you could lead to stalls due to short circuits. So that resulted in a recall of a few 700,000 cars. Unfortunately, fixing these things sometimes is difficult. So same thing happened for a subset of the models with a similar type of thermal runaway. So the previous one was the 2010 to 2014 models. This one was just the 2012 to 2014, some different manufacturing things on, in this case, some solder in that hybrid drivetrain. But again, the fix is a software update. If you look at more aggregate data across different domains, in automotive, if you look at what percentage of recalls by the NHTSA or NHTSA are caused by computer-related or software-related issues, this is essentially the growth of it. So around 30-ish, 25, 30% now are due to these type of issues. And this shouldn't be surprising, right? Why is this happening? Well, we're building these systems in a different way than we used to. They have a lot more software in them. Now things that maybe were mechanical components before are now software. So as the further digitization of things like motor vehicles, medical devices, whatever occurs, it's sort of logical that we're going to have more of these software-related problems. People remember the Toyota unintended acceleration stuff about a decade ago? So there's some misperception that this wasn't at all software-related, that it was perhaps due to floor mats. So Toyota, of course, wants you to believe that still. We have collaboration with Toyota, so not that they definitely, our collaborators denied that this was any way software related. However, if you look at a few points of data, in total, this unintended acceleration stuff has cost Toyota in real dollars about $5 billion. So there's a Department of Justice penalty for in the order of $2 billion, class action lawsuits now in the order of $2.5 billion, plus NHTSA's maximum fines due to some delays in reporting of in the order of $100 million. So very expensive problem. So I think this at least had some things to do with it that were software related. There's a lot of links down here from some of the expert witnesses in this particular case that Toyota lost that was predicated on at least it being reasonable that software could have led to these issues. And if you go look into these heavily redacted slides and things from people like Phil Koopman or Michael Barr, you would see that almost surely there were some software issues. So there's some interesting outtakes of this. Like if you got into this mode where the car would be accelerating out of control, so you can't stop it, if you pumped the brakes, there's a software process that controls the brakes. That process would die and would not restart. So you lose brake assist, and with the throttle fully open to try to get it to get the car to stop with just manual force can't really be done by anyone except for a very, very strong person. So even if you're sort of slamming down on the brakes because you lost brake assist, there's sort of no chance you could stop the car. So lots of interesting examples. Why are these things happening? So I'd argue some of these things are rare. If you look at some recall reports and things like this, you'd see things like, oh, it was a combination of factors that caused this. Things maybe they didn't necessarily test, things that maybe only show up in some scenarios they hadn't necessarily intended. This bottom example, these are both quotes out of recalls of cars from the NHTSA recall reports. The bottom one is something that might happen if you live in a cold climate, if you're trying to get the car stuck out of snow. So you're quickly shifting between reverse, neutral, and drive with the car at high engine RPM. So maybe not a normal test scenario that you'd run across. So the motivation for doing things like formal methods for these things is that formal methods and methods like model checking, I'll talk a little bit more about these shortly, are worst case. So they consider all possible scenarios. So such rare scenarios could be possible to find. All right, so I'm going to skip this example, but another instance of a recall in the aerospace domain. So this is sort of a fun one for an elevator where the doors to the elevator could be open without the car being present due to a software defect. So if you're not paying attention, you walk into the elevator shaft without the car being there, and then you'd sort of fall down. That wouldn't be good. The fire alarm control systems in buildings, particularly buildings like the one we're in, this one from Bosch, this one from Tyco, Simplex Grinnell, this one from Honeywell. These have also had issues either where they'd fail to alarm or fail to notify a fire department for those that have a connection over to the fire department. So the point of listing some of these things is not to highlight a particular manufacturer or a particular vendor. It's just to highlight that these problems are super hard and to give some sort of validation to some of the points I made at the beginning. It's not like all of these companies that have had a very similar failure mode in this product. It's not like Bosch and Tyco and Honeywell that they're not trying to design products well. It's just really hard to get all of these scenarios. When you think about the size of the state space and the size of possible behaviors in modern software systems. It's a fun one. We checked out the aquarium earlier. There were scuba divers. This is a scuba diving computer that could report the wrong tank pressure. So you could be down and then due to a software bug, so you could be too far underwater. You think you have more air left than you actually do. So that's sort of a very interesting, I think, issue, not one I'd thought of. If you look in medical, this is from an FDA report that characterizes recalls of medical devices. Software design defects are now tied with manufacturing defects as the number one reason of recalls of medical devices. And when you think about this, this is actually probably a bit worse, especially for the data period that this covers, which is 2003 to 2012. Right? This is especially bad because at that time, so today there may be medical devices that are purely software, so a program that's actually characterized as a medical device due to diagnostic capability or whatever. But almost all medical devices have some physical piece to it, whether it's a mesh that you implant or a pacemaker or whatever, whereas not all medical devices have software in them, right? So this actually is probably a bit worse than this data would suggest. But that's, at any rate, some hopefully interesting motivation, a few interesting points. So I'll talk a little bit now about what we do for these types of problems to sort of wrap things up about what we can do about this. But hopefully everyone's convinced there are lots of potential issues and that it's a hard problem. Any questions about anything before we go on? Okay, so what we do in our group, so we work on CPS, obviously. There's two domains, fundamental domains we're primarily coming through. It's a branch of these days I'd characterize formal methods as a branch of software engineering. Historically, it would be a branch of theory. And then also a combination of this hybrid systems branch is an interesting field that arose out of control theory and also formal methods. So one of the major Cyber Physical Systems Week conferences is a hybrid systems conference. And then also the systems we're looking at, things like groups of drones, these are also distributed. So this is kind of the background that we're coming from. And then we work in a variety of domains. Obviously can't work in all of them, but the primary ones we've worked in are robotics, aerospace, and power and energy systems. So I've had examples of a few of those so far. And we'll have maybe a few more. So these are some of the robots in our lab doing implementations of distributed algorithms. I think probably, these are from a few years ago now, I think the Perdix video is probably more impressive, deploying drones from a fighter jet with hundreds of them. But the types of things we do, running distributed algorithms for, this is just going to some waypoints, these are going between waypoints, these are mini drones, and this is going between waypoints as well. But so these things are coordinating to do some group maneuvers, and we're looking down from a ceiling-mounted Connect. Okay, and we have a nice simulation framework for this thing. So that's the type of system to keep in mind. So what is this formal verification problem? So building on our earlier introduction to this area, so what we try to do is we have a system model, we have a specification, and we'd like to check if the system satisfies that specification, or if not, know why. Well, what is the system model? What's A? What's P? These things can be defined in terms of a formal syntax and semantics. And that would allow us to rigorously define what it means for the system to satisfy the spec. And then how could we do this? And how could we do this automatically or algorithmically, if it's even possible? So I'll talk a little bit about what the types of specs are, what the types of models are, and then a little bit about on how we can check that. So there are a large variety of techniques to try to check that does A satisfy P. Some of them are formal, some of them are not formal. So the most commonly used ones are not typically formal, so things like simulation. So I know this is the Sim Center, so I thought I'd shout out to simulation. So some of what we do in formal verification for hybrid systems relies on methods that would be used in some simulations, things like numerical analysis methods. These systems, we typically, as we'll see, model the physical behaviors of the systems using differential equations. So there's a lot of numerical analysis that would show up in simulating those things, or in doing formal reachability analysis and other methods for analyzing those things. So this is nice, scalable, parallelizable in a lot of cases, a lot of benefits of this. But the downsides are it has no guarantees in terms of the soundness or completeness of the method. Right? So there's a famous saying from Dijkstra, it's very similar to testing. So what's a test case or a unit test? Well, you're testing a function or a program on one input. So all you know is whether, the quote from Dijkstra goes like, testing can only confirm the presence of bugs, not establish the absence of them, right? Something along those lines. You're just testing one case. How can you know if some other case works properly or not? You try to generalize and say, well, I tested all these edge cases, so things are good, but maybe you missed something. So the formal methods approach typically does some kind of state space analysis of the models, typically using algorithms called model checking algorithms. And these systematically explore all of the possible states that a system can get to. So it has scalability issues, and it has some areas where it can be applied successfully. But some system with 1 million lines of code, this is realistically never going to work for that. So you'd use it appropriately within certain submodules. And again, I just want to highlight this is widely used in semiconductor industry, which is the sort of big impact of this whole area, is that all the modern semiconductor design companies use software tools. They used to develop them in-house, but these days they buy these in EDA packages from Cadence, Synopsys, and other places. This is surprisingly not well known even amongst computer scientists. I always meet people who are not aware of how formal methods are used, so I like to emphasize this. So for CPS, we don't have yet, we're not nearly as far in CPS as we are within I would say, simpler model, which is digital logic. So the digital logic models of what the systems would be things like state machines. So for CPS, we have a lot more complicated situation. If we want to do formal verification, let's say of collision avoidance, of some kind of robot group motion coordination thing, like to get them to form some shape. I mean, we need to model the physical world, we have to model communications, we have to model so many things. We have to model the software. So the abstractions that we would work with are not as clean as what can be successful when we have that digital logic and finite state machine type of abstraction that's successful in semiconductors. You can do things by hand or using interactive or automated theorem provers. These are a few of the widely used ones. PVS is used at NASA a lot. And then you can just do testing. Then there's some other things that can be done, like static analysis, either formally or informally. So if you use tools like Lent, that's an informal static analysis tool. But things like Facebook's FB-Infer is a sort of formal methods-based static analysis tool. In their case, it's either for Java, script, or PHP. Okay, any questions? How are we doing? Friday afternoon? Okay, all right. So I'll tell you a little bit about how we model systems in CPS and then some of the methods for analyzing them. So this is a simple example of something like the thermostat and heater in this room. So this is an example of a hybrid automaton. So the way to think about these, I think I'm going to use my pointer. Yes, because the laser pointer's not as good. The way to think about these things, this is a finite state machine. But it's augmented with a set of real valued variables, these x's, that can evolve continuously over intervals of real valued time according to some ordinary differential equation. There's some generalizations of this to allow more non-determinism. This could actually be a differential inclusion, not just a differential equation. So what this would look like, the initial state of this and the initial condition for these continuous variables, we start off with this thermostat off. And what this is modeling, say, is the temperature in this room. So that's what's on this y-axis, and the x-axis is time. So we'd start off. So this would be cooling according to Newton's law of cooling. Then if we were to get too low, below this T-on point, we may turn on let's say if we're cooling, I guess turn on the heater. But we don't have to. There is some non-determinism allowed in these models. We may turn on. So we may go from off to on if this condition is satisfied. But at the point where we would violate that x has continued to decrease, the temperature is still going down. So if it got to be where x is at Tmin, then we must move. So we'd have a switch over to this on mode. And then this type of behavior could continue with the may and must semantics with this text on this is called a transition, the arrow in the state machine. The text on this is called a guard condition, and this says, okay, this is a may condition that if x is less than or equal to t on, we may move. But we don't have to yet. But if this invariant condition, that x must always remain larger than t min, if that's violated, then we must move. So when we'd move to on, then we've turned on some heat source, so now the temperature, instead of just decreasing according to whatever the ambient conditions are, we're adding heat back or adding energy to the system. So it increased back up for a while until something would go back. So these things are called hybrid systems because or in this case, this is a formal model called a hybrid automaton, but the general field of modeling CPS, the core field is from hybrid systems. And it arose out of needing to model both software state, which you can model with state machines nicely, and discrete behaviors and transitions, as well as continuous state, which typically modeling dynamical behaviors in the physical world, you model with differential equations. So that's where the hybrid nature came from, in that you have both continuous and discrete states and behaviors. Any questions on this example? And there's a way to formalize the semantics, but it's, nobody wants to see that at close to 3 on a Friday afternoon, I'm sure. But you can build up a nice formal semantics. So these behaviors then, I'm going to skip my next slide where I do define what this is. The way you think of this, just think of this like a run of a program, or if you like time series data, you can think of it like time series data. But this is called an execution or a trace of this model. And what that is, it's a sequence of the states that are visited by the behaviors of the system. So by the solutions of the differential equations with respect to time, and by the transitions that occur moving back and forth between the discrete states. All right, so you formalize that as a mathematical sequence, and that would be the behaviors of the system. So starting from some initial point, where can you get? So pictorially, what that would look like, let's say I'm in now an abstract state space. So that would be, for our heating thermostat example, that would be the real line plus those on and off modes for whether the heater's on and off. So whatever the state space is, all this generalizes to complex systems, n-dimensional state spaces, as in if you do any control theory type stuff, whatever r to the n. So the problem then for checking safety properties is starting from an initial state. In our heater example, we were off and the temperature started at some particular value. We follow that sequence of behaviors, and we ask whether we can get to a region that would violate that specification. So all of the possible places you can get to from a set of initial conditions is called the set of reachable states. There's a way to define this formally, but starting from the smaller initial set of states, by following what the program can do, where can we go? So that would define a set of reachable states. Then let's say the specification that I care about for this particular model is that the temperature is always bounded in a range. Like the temperature is always between 60 and 70 degrees, even though it's negative 50 outside, let's suppose. So that heater turning on and off, it turned the heater on for a while, presuming it can add enough thermal energy, the temperature would go up. But we really don't want it to go less than, say, 60 degrees, because then things are getting too cold in the house, and we don't want it to get too hot either, right? We don't want the temperature to go over 70 because it gets uncomfortable. So that specification is an example of a safety specification, and you can represent that as a predicate within the state space. So just think of this as some other set of states. So this would be all of the states in the state space for our thermostat example where the temperature is between 60 and 70. So if this set of reachable states, so that's wherever the system model could drive us, if that set is contained in this other set P, then we're good. Then we would have verified this. So the question then would be, how can we implement all these things? How can I implement a computation of this set of reachable states? How can I represent the system models? How can I do these types of computations? But mathematically, this is what would be going on. So how can I check this? How can I check if the set of reachable states is contained in some other set? So I need algorithms for all these things. And what this would ensure, if we do that, is that there is no execution or trace of the system starting from an initial state that would take us to states where we violate that specification. So in other words, there's no way to leave this set that satisfies, for a thermostat example, say that the temperature is between 60 and 70 degrees. So I can't go lower than 60, I can't go higher than 70. So the way most of the algorithms work for this, and you have to come up with ways to represent states and things, but you'd start with a representation of the set of initial states, and then you would iteratively, typically in a kind of breadth-first manner, you can do this in a depth-first manner as well, you'd compute frontiers, so you'd see where things can be reached.
For a second, I think we just died.
Oh. Oh, no problem. Any questions while we wait?
I have a question. So about more than half a year ago, TVA, they have a problem. They have several computers try to control the flow of their cooling system for the nuclear plant.
Oh.
So
Very Right.
several computer systems. So some computer they just reboot every 2 or 3 years. So they did some average. On average, there's one reboot per machine per year. So they identify several possible reasons. One reason is software related reason. Another reason, like maybe vibration caused, for example, power break. The third reason is like a vibration, accumulation of radiation particles. So what do you think of that?
I mean, I don't know, but it could be these things. Sounds sort of cyber-physical if it's controlling a nuclear reactor or something. I mean, Vanderbilt has this Center on Radiation Effects called ISD. They do a lot of space and defense things where environments are harsh and you can build up, particles and things, ionized radiation. And can cause bit flips and all sorts of stuff. I mean, I don't know. The accumulation sounds interesting, but I don't know. It sounds like an interesting CPS example, though. Could be software related, could be physically related. Yep. Yeah, sure.
In that initial condition space, things that are arbitrarily close to each other in that initial space might produce arbitrarily different outputs, like from a chaos perspective, like a fractal. So I'm just wondering, how do you sample your eye space to make sure you actually know that you're have coverage?
Yeah, so it's a good question. So so I don't think I talk much about it, but the way that these methods work, these are symbolic representations of states. So the way you should think about it, there's no sampling. It's very different than like Monte Carlo or something, where you'd sample a space and then run trajectories forward. This would be really like, for our thermostat example, suppose that initially the temperature could be between, 65 and 67 degrees. You'd symbolically represent that as an interval. So you'd consider all of the points in that simultaneously. Okay, yep. Yeah, so it's a symbolic representation, yep. But then you'd propagate these symbolic representations forward according to the behaviors of the system. And then you'd check if once you compute all these, if the intersection with the negation of our safety spec, so the negation of the safety spec essentially is our bad state. So if that intersection's empty, we're good to go. Okay, so we have about a couple more minutes. So I'm going to skip a couple. I'll come back to our example, though. So what would that sort of look like for our example? We'd have some initial temperature. Let's just say it's a point. We'd see where we can get according to the dynamics. So if we started there, we'd just have, I think in this case, we're starting on, so we're turning up the temperature. So that could increase up to some point. Then we'd have to have a transition. You take the intersection between the invariant of the guard and of the old location. So this would be that new set that I'd propagate to where we could go. And then you'd repeat this. So that's kind of how it would do, and that would be called this flow pipe construction. So that'd be a sub-method used. Okay. So I have a lot of other stuff I can talk about, how we can do this in the context of learning-enabled components like neural nets, but a similar idea can be applied in neural networks. We've done some work on this. If you have a feed-forward network, you can imagine that network is just a mathematical function. It takes inputs from some space and maps them to outputs in some space. It has no internal state. For recurrent networks, you have to do something else. But essentially, this is then analyzing from a given set of points in that input space, where could we go in the output space? So it's essentially doing the range or image of the function, identifying that computationally. And you could formulate things over this to see if a neural network could ever produce behaviors outside of some desired range for feed-forward networks. So this type of approach now has been applied. This is a very sort of hot area within verification right now. We've written a survey paper that has 150 references in it, so it's like every week there's more papers on this. But this has been applied in the context of image analysis, trying to establish the absence of adversarial inputs for a classification method. This has been applied in some other systems as well. The latest variant of the FAA's collision avoidance protocol for aircraft is called ACAS and ACAS-X, which replaces the older system called TCAS. Planes basically have collision avoidance systems. They're like yelling all the time, right? So if you can hear another plane, it's bad because you mean you're hearing somebody else yelling. So that the transponders, you need to do something if you get too close to another plane. So the latest variant of that actually is based on neural networks, which is a little terrifying for various reasons. But that actually had to do with a computer performance limitation in that the way they had designed this protocol, it was huge, like terabytes of memory would have been needed. So they had to approximate it with a neural network. But at any rate, these adversarial questions became important for it, so that example has been verified with this type of a methodology. Just to give you an example of what that would look like for a neural net, if my input space for a three-dimensional, very small network is some kind of a cube, what would the outputs look like? So that's what's demonstrated in this. If I have two output neurons, in this case I think it's 7 layers with 5 neurons each, essentially how can that transform that quite regular input set in the output space? And a lot of the results in this area right now are only for these rectified linear unit activation functions, which some people may know. It's a very popular activation function in neural nets. So there are some controllers where the controller in a control system would be represented as a neural network. And you can do similar types of analysis, combining the analysis I just talked about of the controller with that type of reachability analysis we talked about in the hybrid automaton example for the plant. So doing closed loop analysis to check closed loop behaviors. Okay, so I'm going to skip forward a bit. I have a lot of other stuff. I never know how long we'll talk for. And I'll see what questions there are. I can tell you all about hyperproperties too if you're interested. What I'll close on, this is a link to our survey that we've written in this area for machine learning and autonomy verification. I'll mention a couple programs that are broader that are exploring this, either collaboration opportunities or for other things. So we're part of DARPA's Assured Autonomy program, which is a large project. A variety of aerospace vendors are also involved, so platform providers, Boeing, Raytheon, HRL, some other folks. So the goal of that program really is to answer this question, can we trust autonomous systems, right? Whether it's a vehicle, whatever it is. Because the adversarial examples indicate we can't at this point, plus just normal software type bugs indicate we can't necessarily. There's another program at DARPA called Explainable AI that's trying to get methods from AI that can explain how they're doing decision making, right? So actually have human interpretable way of understanding how a decision is being made. There's some NSF programs, a new program called Formal Methods in the Field that is open to a few different sort of application areas of formal methods, one of which is machine learning, some others are networks and operating systems, but applying formal methods, essentially trying to help move the application of these methods that have been very successful in the semiconductor area into other areas, whether it's CPS or machine learning or OS or networks. So within this context, some of the long-term issues are how can we specify correctness for machine learning components? I mean, what does it even mean for an image classification method to be correct? Like, what's the specification for that? It never misclassifies an image? How are you going to write that down? I can say that, but I can't formalize that in any way, right? Sort of what does that mean? So there's probably some new ways to actually specify things that are necessary, in addition to analysis improvements. Okay, so I'll quit talking because we're out of time, but I'll see if there are any questions. So thank you for listening. Thanks to our group, our students, sponsors, and everyone. Okay.
Here, we got it.
Yeah, I have a question about the verification of the neural network result. Neural network is not okay. So how do you just give like the formal description about the correct the output of the neural network? Because we don't know that.
Yeah, so for a feed-forward network, I think of it as a function, right? It maps from some input space to some output space. So the specification would be in the output space. So if I can compute the range of the function symbolically, so I know every point it could get to in the output space, then I can talk about specifications in the output space. So I can say, no, the output of that network cannot be greater than this or less than this. So this is an example. So for this input set, this is a symbolic representation of the input set. So this is some kind of cube or something, right? Then this set, this union of polytopes, this is all of the places that this network could take you from any point in this set. So that's what this thing represents. So if my specification is that y2 is never, greater or less than something, then I can check that. So that's what it means. It's not clear if this is that useful of a class of specifications, but it can at least let you do range checks on networks.
Okay, in your case, you use this one is I think how about the other like neural network? We have a lot of like the CNN, like the RNN. Have you used the?
Yeah, so for recurrent networks, you can't think of it quite this way, right? Because the way I think of recurrent networks is that they're stateful, right, because of feedback. So we've thought some about it. The things we've thought about aren't going to be scalable. So one way you can think about recurrent networks is from a biological sense and model them as differential equations. And that's how you're modeling state. But that won't be scalable. You wouldn't be able to scale to anything beyond small networks. So I'm not sure. For convolutional nets, we've looked a little bit at it. I think that may help with scalability because that's essentially how they're operating, right? They're made for scaling up for images and things by considering pieces of the image and whatnot. So that may, like working in a feature space essentially as opposed to the whole state space or input space of the system may allow methods to scale up. But right now there are no results on these things, none. Not from us, not from anyone. So this whole area of formal verification for neural nets and stuff really exploded in the last 1 year. There were a couple of papers at one of the verification conferences, and now they're showing up in AI conferences and other places. So I'm happy to send our survey, but right now I don't know of any results for things other than feed-forward networks. And I think the specification question is sort of a deep question. It's not clear. What is it? How can I write down an image classification method is correct? It doesn't make sense, right?
Thank you.
Okay, thank you.
So I'll try to not be too active here. It seems like a lot of what you're saying is it's important that we choose the proper way to approach a problem. And we're seeing a lot of diagrams and a lot of metaphorical application of how you approach a problem. How are you sure you're choosing a model that's simple enough while also being rigorous enough to approach the problem?
Yeah, so for CPS, I don't know, right? So what really needs to happen and what doesn't happen enough in the field is model validation. So for digital logic, a state machine abstraction of a digital logic circuit is almost a perfect abstraction, right? A state machine, a finite state machine, represents a digital logic circuit, whether it's combinational or whether it has state, right? So whether it's sequential or combinational. So for CPS, it's not clear because you have all the classical model validation problems you have of trying to model anything in the physical world. We were trying to create a predictive model from something, and how good is it going to be? The real world's complicated. So this kind of demonstrates it. I think more work needs to be done in this area. So this is a particular kind of power converter. It's a switch mode power converter called a buck converter. It takes a voltage, say 20 volts, and would convert it to some lower DC voltage, like 10 volts. So these show up all over the place in modern electronics, phones. You have a bunch of these in your phone. Computers for doing voltage level changes and so on. And they're more efficient than non-switch mode converters, which is why they're used. So it doesn't really matter exactly what it is, but the point I'll illustrate is we do this type of reachability analysis. One representation of this using a particular tool, unfortunately named SpaceX, not the company, it's out of France, is where this tool is from, Space Explorer, State Space Explorer. So you start from some initial condition, initial states or set thereof, and this gray region represents all of the reachable states of this system, right? So the model of this is some switched differential equation, essentially. So like our thermostat example. Either the switch is open or it's closed, right? On or off, that's it. And it's a power transistor, really, and whatever. So this is a model of this. This is an okay model. But if you actually run an experiment with hardware for one of these converters, that traces in red. And as you can see, there's a little bit of a point where that red trace is not contained in that set of reachable states. So what that means is our model this is a linear model. It's not capturing any higher order effects. And you can also just compare some other simulation behaviors which look sort of perfect to this experimental trace, and you can see they're not perfectly lining up. So in the real world, a real converter doesn't perfectly match the model. So I think this is a major issue in all of CPS because we do analysis of abstract models and stuff, and it's not necessarily clear that actually it's going to apply to real systems. So I think it's a great point. I mean, it's definitely important, especially for moving this stuff to being applicable to real things. Yeah, so I'm not sure we're solving that problem totally yet, but it's definitely a problem that we know about and need to solve. Thanks.
Any other questions? You can stay after and speak with our visitor. He's not leaving immediately, at least like 4:30, so please stay after.
Yep, happy to chat.
Another question?
Oh no, sorry, I said yeah, I'm happy to chat.
Let's take our speaker and then you can all go.
Okay, thank you.